the eigenvalue problem. Okay. Right. Thank you, Zoom. I'm going to be talking about how to move the analytic eigenvalue problem of the Laplacian into a combinatorial setting. And the main idea behind doing this is the fact that in our analytic setting, you're dealing with infinite dimensions, which in terms of your functional analysis can get quite involved, compared to the combinatorial side, where we only have finite dimensions, and hence the problem is much more tractable. And particularly, you might even be able to use a computer to develop some numerical solutions to it. So the key idea I'm going to try and get across in this talk is this linking of analytic objects to combinatorial ones. And I have written up a summary of the key ideas we're going to go through, and particularly how they link up, what's the analytic side and what's the matching combinatorial side. And we're going to spend a bit of time going through these and explaining these concepts. And the reason for that is because I hope that perhaps in your own research you might be able to see how some of these ideas might be of use. So I think the constructions of them are quite useful to understand in a little bit of detail. This will then bring us to the main theorem of the talk, which is the main result that I was able to prove in my master's thesis that I've been working on. And as a result, well, the proof in particular is a little technical. I'm not going to spend much time on it, but just highlight a couple of key steps along the way. Now, I do wish for this to be an interactive session, so if you do have questions, feel free to ask in the middle of the talk. Probably if you unmute yourself is the best, because I think checking the chat is a little difficult. So without further ado, let's make a start. So we're going to have MGVA connected, smooth, closed, so in particular compact, as well as oriented, Riemannian manifold, and the dimension of our manifold M is going to be capital M. And we're going to consider on this manifold the space of smooth differential forms, and we're going to consider the complex value ones. And on this space of differential forms, so the Q here is the order of our differential form, we have got the usual exterior derivative. So this maps a Q form into a Q plus 1 form, and we have our wedge product, which takes two differential forms and maps them in effect to their product. We've got differential forms, exterior derivative, and wedge product. On this space, we're going to want an inner product. So we're going to define an inner product to be the integral across our manifold of the first differential form, taking the complex conjugate, wedged with the Hodge star of our second differential form. Now, for those of you that aren't too familiar with the Hodge star operator, it's essentially a map from Q forms into N minus Q forms. So if we then analyze this up here, we're integrating over an n-dimensional manifold, we've got an nth order differential form. Now, in the problem that I'm considering, I'm interested in the twisted setting, and we sort of need a twisting term. And the twisting term is going to be some real form, a real one form, and this is going to be the letter A. And with this, we can then twist our exterior derivative, so dA. It's going to be your normal exterior derivative plus I A wedge. So I is the imaginary unit. So that gives us our twisting and our inner product terms. And with respect to the inner product that we have up here, we can then take the formal adjoint. So the adjoint of this is then going to be the map Q plus 1 forms back down to Q order forms. So that gives us our adjoint. And there's a fairly easy expression of this particular adjoint. So this adjoint is given by up to a minus sign, depending on some dimensions, Hodge star of the twisted derivative Hodge star. And this then allows us to define our combinatorial Laplacian, our delta A, the twisted version, and it's defined very much like your standard Laplacian, dA star dA plus dA dA star. And it's fairly well known that this Laplacian is a self-adjoint operator. It's got a purely discrete spectrum, so all of the spectrum are the eigenvalues. They're all real eigenvalues, and they're bounded from below, and there's infinitely many of them. That means we can write them out in ascending order, where we repeat them according to multiplicity. So that gives us our operator and the eigenvalues. Now, the key ingredient of this particular method is the min-max principle. And the min-max principle says the following. So if we have U be a bounded from below self-adjoint linear operator. So just like our Laplacian is, with purely discrete spectrum, so again, like our Laplacian is, so acting on a Hilbert space, on HA Hilbert space, then if we write our eigenvalues in ascending order like we do over here, we know that the jth eigenvalue is given as the supremum over a set of vectors fk in our Hilbert space, the k from 1 up to j minus 1. Then we take the infimum of a non-zero vector, but it also has to be in Q of U. And Q of U here is the domain of the quadratic form associated to our operator U. We want it to be in here, and we want it to be orthogonal to all of these FKs over here for all of K1 through to J minus 1. And it should be noted here that these FKs, they don't have to be linearly independent. And what's the expression that we're taking these supremums and infimums over? It's the inner product of UF F divided by inner product F F. And we can see here that it links the eigenvalues to an expression in terms of inner products. Inner products and norms are essentially the same thing, which means sort of when we later on get to error estimates, which obviously we need a measure of how wrong our estimate is, that's in terms of a norm. And this then allows us to translate and go from those norm and error estimates back into the domain of the eigenvalues that we were trying to calculate.
Sorry, Matthias, just a quick question.
Yeah.
So how important is it that H is a Hilbert space here?
I believe it's quite important.
Okay, because the differential forms won't be a Hilbert space, right? If that's what we're going to apply it to.
So you correctly point out that there's a number of subtleties at play here. And unfortunately, those are actually ones that sort of did somewhat derail the work in my thesis, because of the Sobolev spaces that you sort of end up dealing with aren't quite what you want them to be.
Okay.
But yeah, definitely a good pickup. But there are some subtleties at play here.
All right, cool, thanks.
All right, so that's the analytic side covered. Let's move on to the combinatorial side. And particularly, we're going to be looking at K, which is going to be a smooth oriented triangulation. Triangulation of our manifold. M. So loosely speaking, that means we have some sets A, Q, which is the set of Q dimensional simplices, say sigma. So our triangulation is a simplicial complex. So we've got K, KQ, and sigma. Now, formally speaking, sort of for it to be a smooth triangulation, that's if and only if K is an n-dimensional simplicial complex, that's standard, and there exists a homeomorphism F, which maps from your complex into your manifold, such that for all sigma in our triangulation, there exists some coordinate chart U, where our F of sigma is contained in that coordinate patch, and if we compose the coordinate with our homeomorphism, if we restrict that to a sigma, this is an affine map. And if we sort of chase through, F starts off in K. K is a simplicial complex. By definition, that has to sit in some affine space. We map over to M. Our coordinate charts then takes us into Rn. Rn is an affine space, so we have a map between two affine spaces. It makes sense to ask if that map is affine or not. Conveniently, by a theorem by Whitehead, every smooth manifold has a smooth triangulation. And because our manifold is compact, turns out that our triangulation is finite. So that means that there's only finitely many simplices contained in our triangulation. So that's the basic setup of our triangulation. Somehow we want our combinatorial approximation to improve in some sense. And we do this by refining our triangulation. We subdivide it. And in this project, I made use of the standard subdivision. So let's go through and see how that works. So if we have some simplex, it's completely defined by its q plus 1 set of vertices. So the square brackets denote that particular simplex. And we can consider the midpoints of these set of vertices. Okay, and this is for j less than or equal to k. And obviously when j is equal to k, you're looking at the original point. So then if we look at the standard subdivision of our simplex sigma, the set of vertices of that is then going to be all of these pj k's as above there. And we're going to put a partial ordering on this set. So we're going to say that a pj k is less than a prs if and only if j is bigger than r and k is less than or equal to s. This partial ordering is best seen in a Hesse diagram. So let me write that up for you. So we start off with 0q, 0q minus 1, 1 and q, 0q minus 2, 1q minus 1, 2q, 0q minus 3, 1q minus 2, 2q minus 1, 3q. Now this keeps on going all the way down to a 0, 0, And then we have 1, 1, and we end up with Q, Q over here. And then the orderings is essentially saying if anything is higher up in the diagram, then it's bigger in terms of our partial ordering. And then our subdivision is the all of the upward traveling paths of all possible lengths in this Hesse diagram. So for example, if we consider all of these points, so these diagonal here, that's going to be a q+1 dimensional simplex in our subdivision. We could also consider, for example, these three in here, 3 vertices, that's going to be a triangle. And of note here is that you can also skip nodes. So for example, if we include this one here, we skip this one, but we do include the bottom one, so we're skipping this one. 2 vertices, that's going to be an edge. So you can imagine sort of the bigger your simplex, the more possible combination there are within that Hesse diagram. What does this actually look like in practice? I can draw a triangle for you. So if we consider our triangle, now by the fact that our simplicial complex is orientated, we sort of mean that it's got each vertex has a number associated to it, so we have an ordering on the vertices. And then if we recall, first step of the subdivision was to add midpoints. And then from the midpoints, according to our Hesse diagram, we add extra simplices. For the triangle, we're only adding edges, and we in particular end up adding these edges. Now, if we were to change the numbering of our vertices, we again add the midpoints. But this time, you find that the triangulation becomes this. And if you're really keen, there is a third one hiding there, which I'm not going to draw. But the point is, the standard subdivision is highly sensitive to changes of the ordering of the vertices, and hence the standard subdivision that you end up with can be quite different depending on your choice of ordering. Now, I'm not going to show off my drawing skills for the case of a tetrahedron. Instead, I'm going to show you this picture, and obviously you can generalize this to higher dimensions where it becomes a little more involved to visualize. So that's our standard subdivision of a single simplex. We wanted to subdivide our simplicial complex. Well, that's quite easy. Just subdivide each simplex, and by construction, you will find that any common faces are going to have corresponding subdivisions, and it's all going to glue together quite nicely. So that way we can then define our Kn. So that's the nth subdivision, to simply be having taken n lots of subdivisions of our original triangulation K0, and that gets us our Kn. Those that are a bit familiar with simplicial complexes would be familiar with the face maps. So these are maps that map a Q simplex into a Q-1 simplex. Now they do satisfy some compatibility conditions. We don't actually need to know those, so we just need to know these maps exist. Now, in terms of our triangulation, we just want some kind of a measure as to how fine or refined our triangulation is. And this is captured by the idea of the mesh size. And this is given by Hn. So this is defined to be the supremum over all of the edges in our subdivision, so in K1. And in particular, it's the endpoints of the edge. And we're looking at how far are they apart. So we're looking at the metric, and the metric here is the one that we get from the Riemannian metric on our manifold. So if you boil it down, what's the longest edge in our simplicial complex? That's how large our mesh is. And as you would hope, as we take repeated refinements, if we were to take the limit, we find that our Hn goes to 0 as we want it to. Now, for the calculations involved in my working, it actually turns out that this Hn is not particularly useful. In fact, instead, a beta m is more useful. And this is defined by this equation. So essentially saying, what was our original mesh size? How much has it reduced? Is sort of the idea captured by this beta n. And of important note is that this beta n is always in a half to the n 1. And we can, this bound is going to be critical for later on when we get to the error terms, because the magnitude of this beta n will determine how quickly or if at all the error terms converge to 0 or not. With that out of the way, we can now go on to cochains. So CQ is going to be some cochains and of order Q. And we can think of cochains in two fashions. One is to think of a cochain as being a map from the Q-dimensional simplices into the complex numbers. Or alternatively, you can think of it as a formal sum across all of your simplices, where we have some coefficients, some complex coefficient associated to each simplex. And then how do we get between the two? Well, that complex coefficient is obviously the cochain evaluated at that particular simplex. So that gives us our cochains. From that, we can then define our simplicial co-boundary operator. So delta maps from a CQ cochain, so Q-dimensional cochain, into a Q+1 dimensional cochain. And it does this by taking your cochain and evaluating it at a Q+1 dimensional simplex. So we're going to sum across all the possible bases up to a minus sign, evaluating the cochain which lives in here, giving the cochain that lives in here, and evaluating it at all of the different faces of that Q+1 dimensional simplex. And if you chase the dimensions, you see everything sits in the right spaces. From that, we then move on to a little more complicated construction. We look at the barycentric coordinates. So in particular, you should be aware that the simplex barycentric coordinates are fairly easily found online, but they're not the ones used here. The ones used here are the simplicial complex barycentric coordinates. And they're subtly different, and it actually took me a number of months to realize this distinction, and it caused me all sorts of headaches. Don't make the same mistake. So, simplicial complex barycentric coordinates. So we have our set of vertices, so some P1 all the way up to however many there are. And we remember that we can write a simplex by just its points that define the vertices. Now you notice here that I'm using new, and that's because obviously these points are sitting in here somewhere, and we should need an indexing variable to match them up. So if we have that, we can then take any point P in our simplicial complex, and it can be uniquely written in the following form. So P is then going to be sum across all of our vertices. So mu j's evaluated at the point, which we'll get to in a moment, times the original vertices. So essentially, that point is some linear combination of the set of vertices. And what are these mu j's? These mu j's are maps from our complex into the unit interval, and they satisfy that if you sum across all of them, always equal to 1, very much like a partition of unity does. And they also need to satisfy the following condition. So for all q's, if that point is contained in our sigma, remember we wrote it out in this particular way, then mu j of that point is equal to 0 for all j 1 up to however many vertices, but excluding these vertices over here. So mu 0 up to mu q. And this essentially means that if we have a mu j and we evaluate it at its corresponding point, it's always going to equal to 1, and it's going to equal to 0 if you're away from the vertex. So then these mu j's here are what's known as the barycentric coordinates, and a single mu j is the barycentric coordinate associated to the particular vertex that it came from. So that's the mu's. Now a little later on, we're going to need a different set of barycentric coordinates, and this is where the psi's are going to come in. Now, this can be quite involved to try and get your head around, so it's best understood if we have a look at a simple example. So if we consider, there we go, this simplicial complex, just two edges, and we consider the free barycentric coordinates. So let's have a look at mu1. So it has to be 1 at the point, and it's going to be by the condition 0 everywhere else. And then it moves down in a linear fashion. Likewise, if we consider our, I think my pen is dying on me. If we consider our mu2, it has to be 1 at the point, and it has to be 0 everywhere else, and it moves in a linear fashion. And then no prizes for guessing what mu3 is going to look like. 0 over here goes up to 1 at the end. So these very much behave like your partition of unity do, but they're sort of a little more, let's say, jagged. Now, in a two-dimensional setting, so for example, if we have some surface, we can triangulate that surface, and then we can consider the barycentric coordinates of first here of the red vertex, and think of the height axis here as the value of the barycentric coordinate. So it's 1 at the point, moves down linearly sort of to the local neighborhood, and then it's 0 everywhere else. And similarly, for the blue vertex, we have the same construction. All right, so far we've gone through a number of constructions. We finished the analytic side. There's still a few combinatorial side things that are missing. And the main reason for that is because at the moment, we still don't have a way to get between the analytic and the combinatorial, but we're about to change that. So the RAM map R maps your differential forms, and it maps it into the space of cochains. And it does this if we have an R of a differential form, evaluated at some sigma, that's going to be integrated over that sigma, that particular differential form. Now, if we take a sigma and we write it out in terms of its points, and we associate the barycentric coordinates mu0 all the way up to mu q to each of the points, as we explained, Then we can define the Whitney map. Whitney map. Now, before I get to the Whitney map, I forgot to add, this here is for Q greater than 0. If Q is equal to 0, it simply is evaluating the differential form at the set of vertices. Now, coming back to the Whitney map, so this maps in the opposite direction. It takes space of cochains. Now, you want it to map into the space of smooth differential forms. It doesn't quite. It only maps into the space of L2 differential forms. And why this is the case will be clear very quickly. So if we take the Whitney map of a simplex, it's going to be Q factorial, and then we're going to sum across all of the vertices up to the side, then our barycentric coordinates, so mu j, and then d mu 0, wedge, all the way up to d mu q. But important to note in here, the d mu j, that one is missing. And from this, we can see why we land in L2. Because of all of these jagged points on our barycentric coordinates, this thing is obviously not going to be smooth. So this is for Q greater than 0. If we just have a vertex, then it simply is the barycentric coordinate associated to that particular vertex. So that allows us to map between the space of differential forms and cochains. Now, these two maps, the Riemann map and Whitney map, are actually very cleverly constructed because it holds that RW is equal to the identity. And from this, we can immediately tell that the Riemann map is surjective, and as will be important later, the Whitney map is injective. If we have this, naturally, you would then wonder, what about the other way around? Well, unfortunately, not the case. They're not equal. And this is the sort of fundamental problem of this approximation. So we have the identity in one direction, which means we can sort of get very good approximations. We can model one space with the other, but going back again, we have difficulties, not the identity. Luckily, we can, the WR approximates the identity to arbitrary precision, as long as we have sufficiently fine triangulation. And this is why everything only becomes an approximation. It's not exact. And sort of the difficulty then in, say, arriving at a result using this method is keeping track of that error term. What does it become in your particular setting? So how does WR approximate the identity? Well, it does so like this. So for all integer r greater than n on 2 plus 1, so this comes from a Sobolev embedding theorem, there exists some positive constant kappa independent of our n, such that WR applied to a differential form, take the differential form, is going to be bounded by that constant times the mesh size omega r. So the zero norm, well, that's the norm associated to our inner product. We have our constant, we have our mesh size, and here we have the R Sobolev norm. And we can see that as you refine your triangulation, Hn goes to 0, and WR approximates the identity operator. Now that we can map between our two spaces, we can finally fill in a couple of missing gaps on our combinatorial side here. And the first is the cup product. So much like the wedge product is for differential forms, this maps to cochains and effectively multiplies them together. And it does this in the following way. So a C1 coupled with a C2 is the Whitney map applied to the first cochain, wedged with the Whitney map of the second cochain. So we now have two differential forms. We can apply the exterior product, and then we make use of the Riemann map to get back into the space of differential forms. Likewise, we have a Whitney inner product, and this is defined to be apply the Whitney map to both cochains and use the inner product we had on differential forms. And this is where it's important that the Whitney map is injective, as otherwise this inner product would not be well defined. Now we have our twisting form A. We want some corresponding cochain. We're going to do the obvious thing, apply the Riemann map to it and call it a day. And likewise, we're going to have our twisted version of the combinatorial exterior derivative, and we define this like we did on the analytic side, the original version plus I a cup. So very much the same as on the analytic. And then let's get ourselves some more space. And then with respect to our Whitney inner product, we can take adjoint, so that maps Q plus 1 cochains down into Q cochains, and we get the adjoint operator as well. And from that, we then have all of our ingredients for the combinatorial twisted Laplacian. And as you would expect, delta A adjoint, delta A plus delta A, delta A adjoint. And our space of cochains is finite dimensional, so hence our eigenvalues for the Laplacian are just going to be a finite set. And these are going to be our gamma 1s up to some gamma j. And congratulations, we have made it through all of our notation, which gets us to the exciting bit, to the main theorem I was able to prove in my thesis. Unfortunately, the main theorem that I was attempting to prove and what I was able to prove are quite the same thing. And the main difference is that there's two assumptions that I needed to add. So assumption 1 says the following. Again, for all integers greater than n on 2 plus 1, there exists some positive constant kappa such that the following holds. So D star W R omega take omega. And the zero norm is bounded by kappa Hn D star omega in the R norm. And you can see this is very much like the estimate we had for WR approximating the identity, but we have these extra operators floating around. And unfortunately, as the exterior derivative is not a bounded operator in the spaces we're working with, sort of trying to prove this assumption turned out to be rather difficult, and due to some time constraints, it was left as an assumption. And assumption 2, well, all I will say there is later. At the moment, we don't have the notational knowledge to know what it actually says. So this brings us to the main theorem. And it says the following. So if we have Mg, which was our connected, smooth, closed-oriented Riemannian manifold, we have our initial triangulation K0. Then there exists a positive constant kappa, independent of n, and as long as n is large, so it has to be sufficiently large, and if assumptions 1 and 2 hold, then we have an inequality on the eigenvalues. In particular, we have the combinatorial eigenvalue, and then we have a whole lot of error terms, which I will talk through once I have written them up. And that is less than or equal to our analytic eigenvalue. So in essence, I was able to develop a lower bound for the analytic eigenvalue in terms of the combinatorial one. In terms of the error terms here, we've got that constant kappa. Kappa A is another positive constant. This one is purely dependent on A, so our twisting form. We already encountered beta n. And as we can see, so this term is going to go to 0 as we take the limit. But because beta n is bounded below by 1/2 to n, we see that at best these error terms in here are going to approach a constant, and at worst go to infinity. So it's not quite the result I was hoping for, but this is the best I could do. Now, the whole reason for trying to develop a result like this comes from the work Sararef did in his thesis from 2007. He essentially looked at the same problem, and he was able to derive very much the same result as this. But his result also had an upper bound on the analytic eigenvalue in terms of the combinatorial eigenvalue, and his error terms, all of them went to 0 as you take the limit. And as such, by the squeeze theorem, you then see that the two eigenvalues are actually converged to each other. The critical thing for him was that he was considering the case when Q is equal to 0, so 0 order differential forms and cochains. I, on the other hand, tried to generalize this to higher orders. And as you can sort of see with the assumptions and the weaker theorem, it would appear that it's not quite possible to do that, or at least not using the method that I and Sararef made use of. Now, at the start, I mentioned that I wasn't going to go deeply into the proof of this, and instead I'm just going to highlight two sort of key contributions that I relied upon to get to this result. Now, the first of this is a relation of the barycentric coordinates between subdivisions. So if we say have a Kn and we have barycentric coordinates mu, and I'm going to write this out as a vector, so you have mu1s up to however many vertices you have, transpose, and then you have your standard subdivision, and these barycentric coordinates are going to be psi. And again, we just write them out as a vector, however many there are. If we write them out like this, then they're actually a linear combination of each other. So our mu is equal to 1/2. Now, capital Psi is a matrix I will get to in just a moment, and our vector lowercase psi. So this here is a matrix, and in particular, every single entry is either a 0, 1, 1, or 2. And in fact, most entries are 0 or 1. There's only a single entry of 2 in every single row, and that corresponds to the fact when one of these barycentric coordinates, the vertex that it's associated to, already exists in the original simplex. So that was the key ingredient I was able to show. Barycentric coordinates are a linear combination, and I then made use of this to calculate the growth of the Whitney map. And you can see how I did this in the sense that the Whitney map is purely defined in terms of the barycentric coordinates. If I have a relationship between the subdivision of the barycentric coordinates, well, surely if I just plug that into the Whitney map, do a whole lot of simplification, I get the same, well, not the same, with a relationship, and that's essentially what I did. The catch is that plugging it in is simple. Trying to simplify the expression is quite involved, and that is where a lot of the work and trial and error came about. So, if we have a sigma sitting inside of the simplicial complex. We consider the Whitney map of this, and this is going to be half q plus 1, and then we're going to sum over simplices in the subdivision. Now we're going to have a constant here dependent on both tau and sigma, and importantly, the Whitney map of the taus. And again, we can see that the Whitney maps are essentially a linear combination of each other. Unfortunately, the growth rate here, this to the power of q plus 1 term, is exactly sort of why my error terms don't converge to 0. They're just a fract to, this growth rate is too large. And why did I want to go down this path? Well, the main reason was that using this result, I'm able to pull back all of my error terms, which contain a lot of Whitney maps of summing, and pull them back into the original triangulation. And once they're in terms of the original triangulation, they're a constant. They don't change anymore as you take refinements. Hence, I can absorb them into the kappa term, whilst previously they were dependent on n, and you had to keep track of them. Now that we have this, I can finally tell you what assumption 2 was. And this tells us that for all n, for all q, and for all tau in the subdivision, there exists a sigma in the parent such that eta tau sigma is not equal to 0. And I can explain why I need this assumption quite easily. It comes from the fact that if we have, say, an A not equal to 0, and I want to write this as the product of 2 numbers, both of those numbers can't be equal to 0, and as it turns out, my B is exactly that eta term. I have been able to show that this assumption holds for the circle, and also for the case when q is equal to 0, which is somewhat noteworthy because that's exactly the case that Sarif was considering. He was able to get his results. So that very much concludes my talk today. I hope I've been able to demonstrate to you how you can use combinatorial objects associated to analytic objects and use them to solve a particular problem, so in my case, the eigenvalue problem, and see how you can sort of keep track of the error terms and get an approximation. Hopefully you found that useful and you might be able to make use of that in some of your own working. Now, are there any questions?
Thanks very much for that, Matthias. Dreaming and thinking, Matthias, for a great talk.
Thank you.
Are there any questions?
I just have a quick question. These assumptions, do you have a feeling of whether they will hold, like in general, or do you have no feeling, or?
So I think assumption 2, probably in its current form, probably doesn't hold, but there is some hope in that. So I consider the standard subdivision. If you go to the regular standard subdivision, that I think is more likely to hold. So the assumption would slightly change, but I think that would hold. Assumption 1, I think probably, well, it's a function. So assumption 2 is a combinatorial question. Assumption 1 is a functional analysis question, which is not my strong point. I don't know, but there are some other results, sort of other paths that other researchers have taken that allow me to get the results I need. So there is sort of potential to sidestep that assumption.
All right, cool, thanks.
Any other questions? Okay, I have a question. So you said with your theorem that you were trying to generalize the result of someone else who was working in q equals 0 case.
Yeah.
You said that using the same method, you don't think it's very likely that you'll be able to get a directly analogous result. But you did say that you like, as in, unless you do it in a different way. So like you try to prove the same theorem in a totally different way, I guess. Do you have any sort of ideas or hunches that you're trying to follow, like using a different method to prove the same theorem, or?
So I think sort of the least changing of method would be considering different subdivision schemes. Other than that, sort of the main methods that seem to work is, so the fundamental problem why things don't work is the adjoint operators here aren't, I don't want to say they don't approximate each other, but generally speaking, it's hard to prove that they do approximate each other. Now, the sort of main way that seems to be to get around this is the adjoint over here is defined from the inner product with the Hodge star. There is a combinatorial version of the Hodge star that approximates the analytic version. So if you use that to define these adjoints over here, that seems to be a way of getting you the result that you want. However, all of those papers that sort of go down this path are sort of specific in sort of other criteria. So they don't tend to hold for arbitrary manifolds anymore. They're sort of specific orders or specific dimensions. So it very much seems to be that the summary result is sort of the most general that you can, and any sort of like other generalizations of it, you then do it at the expense of some other condition. I think it becomes a balancing act of what we want.
Cool, very interesting, thank you. Okay, well, I think we might finish up there. So let's thank Matthias again for a great talk.
Thank you.
Okay, so I'll stop the recording.